All right, well, welcome. As I had a feeling, lots more people are joining us online than normal, and that's fine. Welcome, whether you're here or not. I've got 2, 4, 6, 8, 10 in class, and lots of more people on Zoom, so welcome. Let me get this going. So, yeah, exam 3 was Friday. I'm about maybe a third to halfway through grading it. Usually I just sit down on Saturdays and just plow right through it all. But this Saturday I had to drive to Pennsylvania to pick up my younger daughter from college, who spent all semester on campus and is not going back in the spring because they invited they're doing their campus de-densification by the sophomores were not invited back in the fall, and the freshmen are not invited back in the spring. So she got to spend her first semester on campus, but now is coming home. So anyway, that's why I didn't get it graded on Saturday, and Sunday I had some other stuff to grade and wasn't feeling all that well. So anyway, I'm about halfway through it. The odds of me getting it done before you go may not be great, and you're all going home. If you want access to that exam, I'm happy to just send me an email once it's graded. I can scan it for you and email you the scan so you can know exactly what went wrong. Question? Yeah, right. So the question is, are we doing the top hat thing? No. I know that people in here have been asked to quarantine, and nobody's ever come and asked me for a list. And I don't think anybody's going to come and ask me for a list of this class. So I'm just making the executive decision to stop the attendance. No, I'm not going to do it. Right. So other announcements. Kappa 12 just went up. It's due a week from Thursday. It will cover the stuff that I'm going to cover today and the lecture that I'm going to post sometime over the week. Reminder that I do owe you a class. We're a short one. I'm going to post that sometime over the break. I will assume that you have watched that before you come to class next Monday. So please be ready and be pre-prepared and ready to go next Monday. Obviously, there's no class after tomorrow. We're done after today in this class. And then we'll be meeting online. That will be Zoom synchronous, so I'll plan to do those lectures live in some sort of format. I haven't quite figured out exactly how it's going to work, but you'll obviously be Zooming and have a chance to ask questions and interrupt me, and hope. This has been a weird year for interactivity anyway, and it's going to be even weirder once we're all online. But if you have questions, type them in the chat, and if I'm not seeing the chat, unmute yourself, ask a question. It's no different than raising your hand in class. So please interrupt me if you have questions. Moving forward. All right, exam 4. I know we just said exam 3 and it hasn't been back yet, but we need to think about exam 4. At this point, so I told you I had an idea. Here's my idea. Give it as a normal exam asynchronously on the last Friday of the semester. That would be the 17th. Let you pick an 1 hour block window anytime you want. Download the PDF of the exam, work on the exam on your own honor system to not be cheating or working with anybody else, and then upload that exam, the PDF of your work, to a Canvas Dropbox. To disincentivize the cheating and to also make it so that there's less pressure on that last exam, my thought is that we'll have a total of 4 exams total through the whole semester, 1, 2, 3, and 4. I will drop the lowest grade and the highest grade. So if you do decide to go rogue and look up all the answers or work with someone else and do way better than you did on the other 3 exams for this exam, it won't matter because that's the one I'll throw out. If your home situation is horrible and you just can't find an hour to concentrate and you just do horrible on that exam, and you're much lower than your other 3 exams, it's okay because that exam will be thrown out. So that's my idea. Are there any, so there are lots of good things that I just mentioned going along with that particular thing. The downside of that particular thing is, that I can see are, if you're counting on that last exam to raise your exam significantly, you will have a hard time doing that. Your grade will be pretty much, there'll be a pretty small range on which that final exam can actually move your grade one way or the other. But that might be good for you and it might be bad for some of you. It also opens up the possibility if you've got a 95 average in this class, you don't even have to take that final exam if you don't want to. Thoughts? Hearing no vehement objections, it is so moved. Okay, you'll be hearing more from me about that at some point then. There'll be a normal exam like I've been giving, with significantly lower stakes since we'll be dropping the lowest and the highest. Okay, great. Somebody did something in the chat window. Okay, there's another suggestion in the chat window, which I will just lower the weight of the highest and lowest exam grades. It's a possibility. I'll take that into consideration. Thanks for the suggestion. Okay, what do we got up here? Oh, there we are. So let me share this desktop with you. Let me pin this video. Okay. I have posted some stuff on Canvas that you might want to take a look at. We have finished our thermodynamics section of the class. And I promised you I was going to post, I think at the end of the lecture I posted last week, I promised you a video. This is one of the most amazing YouTube videos I have ever seen in my entire life. It is still astounds me to this day. It is acapella science and okay, calm down. Now, how am I going to get this to transfer both to? I'm gonna let you. I'm not sure how to make this go on. Let me see if this works. You're not hearing that over the thing, are you? Okay. All right. So here's what I'm going to do. I posted a link to this thing on Canvas. You can go look at it on your own time. It is the acapella science guy doing 5 different takes of him singing a parody to Billy Joel's For the Longest Time backwards. And he's doing all sorts of irreversible processes like cooking eggs and popping balloons and knocking down dominoes and throwing beads up into the air, right? All these things that are increasing the entropy. And he runs the whole thing backwards. So all of these things, it breaks your brain because all these reverse entropy things keep happening in the video. So it's astounding because it's a really cool video and it explains entropy pretty well and why entropy sort of infers a direction of time really well. And also he had to memorize this thing backwards. He had to memorize the lip sync to this song backwards. He had to film, so they taped it forwards, obviously, and then they play it backwards, but he's singing it forwards in the backwards version. It's crazy. You have to check it out. All right, so that's your other homework for over the break. Share it with your family and friends. It's fantastic. There's also a making of video, which sort of walks through how he does it. And yes, he has some weird knack for being able to mouth backwards words. It's fantastic. Anyway, okay. So we are actually now officially done with Holiday, Resnick, and Walker. This next section and the rest of the sections that we'll do this semester and your entire Analyte 4 class will be out of the other textbook that was on our list for the semester at Thornton and Rex, Modern Physics. So that's exciting. You're finally out of your introductory textbook, physics textbook. It only took almost three semesters to do it. Okay. So we're going to be skipping around a bit, covering some topics that you're going to need to know before next semester. So Thornton and Rex, specifically starting in chapter 3, which is experiments that led to quantum mechanics. And we're going to start with 3.3, which is black body radiation. Now, we've already covered black body radiation a little bit when we talked about radiative energy transport. Remember? We've already written this equation down. And this is the radiative power of an object is equal to epsilon times sigma times its surface area times its temperature to the fourth power. This is the Maxwell-Boltzmann law. No, it's not. It's the Boltzmann law. So remember, for a perfect radiator, we define that by epsilon equals 1, and it absorbs all of the light that hits it. And we call these things black bodies. Because if they didn't have much temperature, they would appear black. So we saw some cool reflective paint, non-reflective paint that you could like Vantablack that you could paint on the surfaces of things to make them appear epsilon equal 1. It turns out that's not really epsilon equals 1. It's pretty close in the visible, but outside the visible it's not as good. And certainly if you heat this thing up, the paint's going to melt off and it's not going to be very useful. So it's not that useful for these experiments to be using Vantablack. What is a better black body? A good example of a black body. Turns out objects aren't all that good at black body. Even the ones we paint, well, those aren't bad. But if you just look at common everyday objects, the reason why we can see them is because some light at least bounces off of them. So you need to get kind of creative to do this. And it turns out that a good example is a small hole in a heated box. Turns out the hole itself becomes a pretty good black body radiator because any photon, any wave of light that happens to go in that hole is going to bounce around in there a lot before it has a chance to come out. And so any individual wave that comes in is unlikely to, in fact, be reflected out of that hole. So the hole itself is a good, I'm going to say BB radiator for black body radiator. Okay, this is in fact how the phenomenon was discovered. Here is an example of that, right? If you have some cavity inside some oven with some hole in it, yeah, the hole itself is almost perfectly absorptive, right? Any light that happens to shine in there is going to be maybe absorbed by these walls, and that's okay, and re-emitted by those walls, and that's okay, but it's going to bounce around in there, and the odds of it coming out that same small hole are pretty small. So this could be a 99% blackbody radiator for all wavelengths, pretty easily. In fact, this is how the phenomenon was discovered, right? People have, for thousands of years, been heating ovens up to very high temperatures for the purposes of casting clay pots and making, even better, making metallic instruments and tools and things like that. So this is how the phenomenon was discovered. That hole will get brighter the hotter you make the oven, the temperature inside it. And interestingly, the color will change too. So if you heat a red clay pot, for instance, in this oven, not blot, pot. The hole, actually, sorry, let's make the cavity itself out of a red clay pot, right? The whole thing is red, made out of some red clay. We're gonna make it a big cavity. We're gonna put a hole in it. We're gonna heat it way up. What color does that hole glow? The hole glows first red, then orange, and then yellow as T goes up. Do the same thing for a yellow clay pot. Hole glows, first red, then orange, then yellow. Same exact thing. It doesn't matter the color of the pot, the composition of the pot, whether it's metallic or ceramic or whatever it is, makes no difference. As you heat it up, a hole in that thing starts glowing red, and then glows orange, and then glows yellow. Color, composition of pot does not matter. Do not matter. Only the temperature. And this is true of all black bodies. So this is a cool thing, that we're getting to some more fundamental law of physics if the composition of the thing doesn't affect how it behaves with temperature. This is an insight into some deeper truth. So we get the total power here, right? We know at a given temperature how much power is being radiated out of a particular cavity in this black body. But what does the spectrum look like? Are all those photons coming out of the same wavelength? Is there a range of wavelengths? What is the intensity spectrum as a function of frequency or as a function of wavelength? Now we want I as a function of frequency or I as a function of wavelengths. We're going to do both of them. But let's think about this qualitatively first. Because the formula is rather complex and messy. But I want you to have in the back of your head how things vary with it first. So as you heat, if you look in the hole and increase the temperature, as temperature goes up, two things happen. It gets brighter and changes color. So here is what that intensity function looks like. Actually, and you can plot it versus frequency or wavelength, doesn't make much difference. It looks kind of like this. And if that kind of looks familiar, it should. It probably looks a lot like the Maxwell-Boltzmann distribution that we wrote down 2 weeks ago now, probably-ish, where we were plotting the probability of finding a particle moving at a particular velocity as a function of that velocity and how that changed with temperature. This is a completely different thing, but qualitatively it looks a lot the same. So that's fun. So it's not surprising that it should get brighter as the temperature goes up, because we already knew that power went up as T to the fourth, right? If you increase temperature by a little bit, the actual intensity and the power coming off of this thing goes up by a lot. But what about changing color? Turns out, if you plot the color, again, you can see a nice yellow here. This is a really hot pot or hot kiln inside of there. And you sort of see, you lose all of the sense of any structure inside of there. It just becomes a glowing mass of stuff. And that's one of the characteristics of black bodies. But this is the actual color on some weird color wheel, which I, don't really, I'm not fully familiar with this particular way of measuring colors, but there's clearly two different axes here, X and Y, and somehow three different colors being plotted, because you usually have red, green, and blue. But anyway, they've managed to compress this into a two-dimensional scale, and you can see how the color of a black body radiator, as seen by humans, will change as you change the temperature of that substance. And so I said they went from red to orange to yellow. I'm talking about increasing from about 1,000 Kelvin to about 4,000 Kelvin, which is kind of the limit of what you can do in a normal, like, I don't know, 2,000 years ago, perhaps, oven, which is still pretty good, right? That's really hot. That's way hotter than the fire you're going to make in your backyard. So you can see how it goes. So this is at very low temperatures, things don't glow at all, right? We are at very low temperatures. We're at room temperature. Turn off the lights, we're not glowing at all. As you start to heat a black body radiator up, it will glow a very dull red at first. And as you heat it up, it will get brighter and brighter and brighter and change color from this red to this orange to this yellow. And if you keep going to this even green and blue, and if you keep going to T equals infinity, there comes a point actually where you're not changing the color anymore anyway. But you end up in this blue region over here, which is a little bit backwards than how you would normally think about it, because we've been taught by colorologists that red colors are cool colors or warm colors, and blue colors are cool colors. And that may be true for your environment, but the opposite is true for actual things that are hot and glowing in our environment. The hotter it is, the bluer it looks. The cooler it is, the redder it looks. In fact, stars are decent black body radiators. If you go out, you can actually see, go out tonight, if it's clear out, and look at Orion. Orion, three beautiful belt stars all in a row for Orion's belt. Orion has a very red star for his head, Betelgeuse, and a very blue star for one of his feet, Rigel. That's very specific temperature differences between those two stars that you can see just by looking at those two stars. Betelgeuse is much cooler surface temperature than Rigel does. So that's useful. Okay, so can we characterize this changing color? Yes, we can. We can characterize the changing colors by something called Wien's law. This was named for Wilhelm Wien. Wien, I think, was a German or Austrian or some Central European. So the W is pronounced with a V. Wien's law. He won the Nobel Prize in 1911 for this and other discoveries. And Wien's law goes like this: lambda max times T equals 2.898 times 10 to the negative 3 meters Kelvin is a constant. I don't know why. Almost every other constant that you write down has a symbol and a name that you usually write down. This is one of the exceptions. I've never seen a symbol for that number. It's just always written as that number. So anyway, what is this lambda max thing? Is the wavelength of the peak of the distribution. So two things happen when you heat up a blackbody radiator. It gets brighter at all wavelengths. So here are several blackbody curves for different temperatures. We haven't even changed it. We actually doubled the temperature and going from 900 to 1800. Two things happen when you increase the temperature of an object. One is it glows brighter at all wavelengths. This 1200K curve is above the 900K curve at all wavelengths. And you can see how doubling the temperature from 900 to 1800 can give you a factor of 16 increase in the power. This is really is a T to the fourth law because you've got so much more area under that top curve than under the bottom curve. It's a huge difference. So that's one thing. It gets brighter at all those wavelengths. The second thing is that the wavelength at which the peak happens shifts towards shorter wavelengths. Right? Here's the peak here, a little less than 2. For the 900 one, it's just a little less than 3. And that's what Wien's law is telling us. Lambda max is where the peak of this distribution happens. And as you increase the temperature, you have to decrease lambda max. So again, increasing the temperature, making the object brighter at all wavelengths, and shifting the peak wavelength towards shorter wavelengths. Okay, and it's a constant. So yeah, T goes up, lambda max has to go up. T goes down, lambda max has to go up. And it's pretty easy to figure out what the number is. Okay, so now people had been measuring this. They sort of knew qualitatively what it looks like because you can do experiments to test that out. Now theorists went to work to try to figure out the full functional form from first principles of what that distribution actually is. So we need to know what I as a function of wavelength is. So the best early equation was called the Rayleigh-Jeans formula. And there was a guy named Rayleigh, obviously, who found it should go as wavelength, should be proportional to wavelength to the negative fourth power, and somebody named Jeans came along and figured out what the proportionality constant had to be. And here is that formula. I as a function of wavelength and temperature is equal to 2 pi CKT over lambda to the fourth power. So you've got your 1 over lambda to the fourth power, consistent with what Rayleigh found, and Jeans figured out what these proportionality constants had to be. Great. So what does that look like? Well, you can already see some problems with this, right? Maybe. Can you already see a major problem with this formula? Again, this came from some theoretical understanding of how the wavelength should fall off as you go towards longer wavelengths. So how the intensity should fall off as you go to longer wavelengths. What happens to this formula? It's a 2 pi c, as in the speed of light, k, as in Boltzmann's constant, t, divided by lambda to the fourth power. Right. So these are all constants except for t and lambda. So what happens to the intensity as wavelength goes to 0?
It rises infinitely.
Bad things happen. It goes to infinity, right? If you, as lambda goes to infinity, lambda goes to 0, I goes to infinity. So this is a problem. This is the Rayleigh-Jeans formula. You can see when you get out towards long wavelengths, it actually doesn't do a bad job of describing what's going on here. But the Rayleigh-Jeans formula shoots off to infinity at small wavelengths. And we know that that doesn't actually happen. That it actually bends down and turns over actually even after a while. So this is a problem back in the early 1900s. It was a problem known as the ultraviolet catastrophe. People were rather worried about this. They were afraid physics was broken and they'd never be able to solve this. Catastrophe may seem like a hyperbole now, but people were really worried about this 100 years ago. So how is this Rayleigh-Jeans formula thing derived? Problem, it goes to zero, goes to infinity, I goes to infinity as wavelength goes to zero. And this is a problem known as the ultraviolet catastrophe. Ultraviolet catastrophe. Ultraviolet, because ultraviolet are the lower the wavelength than visible light particles or wave. Okay, so how was this derived? Basically, it took, so it was derived by considering standing waves of electromagnetic radiation inside our cavity. When you do that, so again, we've got some hole, and we've heated up the walls of this cavity, and we've got electromagnetic waves, light waves, being emitted from one wall and interacting with the other wall, and you've got some standing wave there, right? So as the wavelength increases, fewer states become available. Right? If my cavity is 1 meter in diameter, and I've got, you know, a ½ meter wavelength wave, I can only get so many of those in there. And if I go to even longer wavelengths, there becomes a point at which I can't fit any of them in there because the wavelength is longer than the cavity itself. And so for this reason, as the wavelength increases, the number of possibilities for having that wave contained inside that cavity go down. And so that's why the intensity goes down as a function of wavelength. But the problem is, as wavelength goes down, there are more and more and more states available. And there's nothing to stop this thing from happening. The shorter wavelength you go, the more wavelength states you have, and it eventually goes to infinity, which is our ultraviolet catastrophe. So the problem comes in these very small wavelength waves and these very high energy situations then, or very low energy situations. Okay, along comes Max Planck. Planck started by stating that there was a minimum value of the energy associated with those oscillators. So again, how do you get a plane wave propagating inside a cavity? Well, you need some sort of electrical oscillator at one end that's going to start that plane wave. And then it needs to have another electrical oscillator over here to reflect that plane wave back. So you've got a whole bunch of oscillators that are oscillating at various frequencies associated with the wavelengths of the waves that are actually being produced inside that cavity. Okay? They didn't really know what these oscillators were, but they knew they must be there because that's how you generate electromagnetic waves. You need some sort of moving charged particle or charged whatever, oscillator. Okay, so Planck started by stating that if there were a minimum value to the energy of these oscillators, I'm going to say oscillators in wall of cavity, then you could get the function to turn back down at small wavelengths. Empirically, and then from first principles, he determined that I, as a function of wavelength and temperature, must equal, and this is the Planck law, 2 pi hc squared divided by lambda to the 5th power, all times 1 over e to the hc over lambda kt minus 1. So this is fascinating. There is a new parameter here. Let's call it hc over lambda. H times f, or hc over lambda, is some minimum, is that minimum energy. Planck, when he set out to do this, assumed that he would be able to, mathematically, set h goes to 0 and arrive at some useful functional form of this thing in the end. Planck assumed that if he set h goes to 0, he would get a reasonable solution. He did not. He was never able to make h go to 0. It only works if h has some non-zero quantity and some non-zero value. And this disturbed Planck to no end. He was not setting about to create a new branch of physics. He was not setting about to, he was just trying to explain why this thing turned down at low wavelengths. And he introduced some artifact, meaning this minimum energy thing, into his equations to make it work, and he wasn't able to ever get rid of it. So, amazing implications. New fundamental constant of the universe. We call it Planck's constant, after Max himself. And as you know, today, h is 6.626, throw a 1 there, times 10 to the negative 34. It's a really small number. Don't get me wrong. It's a really small number, but it's not 0. Joules times seconds. This implies a minimum energy for any state E min equals h times frequency, or h times c over the wavelength. Because these are frequency and wavelength for electromagnetic waves are related by the wave speed, which in this case is the speed of light. It also implies that's weird. There is some minimum energy to the universe. You can't go below a certain energy level, which is weird. And it also implies that energy comes in discrete packets, that it's not a continuous thing. that the minimum delta E is also this thing. You can't change your energy by an amount that's less than this amount, or that's not an integer amount of this amount. Also implies that energy is not continuous. In other words, En, the nth energy state, is n times h times f, where n is some integer value. These oscillators in our walls can only emit or absorb energy in discrete multiples of that. Delta E equals h times f. Planck was deeply disturbed by this. He really didn't want nature to be divided into discrete packets of energy. But it turns out that's exactly what happens. So this whole thing, of course, leads to quantum mechanics. And this is where you're going to be probably starting your journey next semester with this sort of beginning. These are some of the experiments that led to the beginnings of quantum mechanics. And of course, this implies that light waves themselves come in discrete packets with discrete amounts of energy. Yes, you can describe a light wave as in a classical thing, but at its core, a light comes in discrete packets. And we call those discrete packets photons, or particles of light. And so all of this is sort of implied by there being a minimum energy to those oscillators and a minimum delta E that those oscillators can possibly have. Okay, it's also going to be useful to know the Planck's law for frequency space, I f t instead of I lambda t. Usually you'll write a little subscript f here because these are fundamentally different things. I'll get to this in a second. Measuring the same thing, this is intensity as a function of frequency now, though, instead of intensity as a function of wavelength, you get 2 pi h f cubed over c squared, and this becomes 1 over e to the hf over kt minus 1. Now you might remember and be a little bit confused by this because original thing had a c to the 5th, c squared and a lambda to the 5th here. This one has frequency to the 3rd power and c squared on the bottom. So what's going on? These two things don't even have the same weight, same units. I'll just write it down here so you can see it from above and compare them directly. I lambda t, same function, well, same phenomenon, 2 pi hc squared over lambda to the 5th power, 1 over, this is basically the same, hf, or hc over lambda kt minus 1, right? So this is, the 1 over x e to the term is about the same. But look at this, you look at these terms up front. You've got an f cubed over c squared over here. You got a c squared over lambda to the 5th here. This is not just substituting in c equals f times lambda and substituting lambda for f. You have to be more careful than that. This is a more fundamental difference between these two things than just making that swap out. So yeah, so you might have thought that you were going to get an f to the 5th term here, but you only get an f to the 3rd term. Why is that? remember, I lambda is per unit wavelength. And IF is per unit frequency. So these are somewhat fundamentally different things because you're doing the counting differently. As with the Maxwell-Boltzmann distribution, again, what are the odds that you're going to get let's go back to our functional form. What are the odds that you're going to get a wavelength 4,000 nanometer photon with this particular temperature blackbody? Exactly 4,000. 0, right? This, like the Maxwell-Boltzmann distribution, is a distribution that's meant to be integrated. So you really have to integrate this d lambda in order to get a probability of getting a particular photon in that particular wavelength range, right? And you have to integrate this one, d frequency, to get a probability of finding a photon within a particular set of frequencies. So that d lambda and df are sort of built into these equations anyway. And so not only are they have units that are per wavelength or per frequency, but you kind of have to multiply them by a d lambda and a df also to get the units to work out to be the same. And so that's why there's fundamental differences between these two things. They can't just come down to replacing lambda with f. Also, we know, let's say, as with the Maxwell-Boltzmann distribution, have to integrate to get I. So d lambda and df are important parts of the equations. I'll say important pieces. And we know lambda equals c over f. So we know that d lambda df is equal to negative c over f squared. And that's actually where that missing f squared term is. It's in the converting the d lambda into the df times, so d lambda equals negative c over f squared df. And that's where that f squared goes to. What's the negative sign tell us? No negative signs are showing up in there because we don't really care about it, but it does tell us something. Basically, that's just you're counting in the opposite direction, right? Wavelength, as you go up in wavelength, you're going down in frequency. And so it's just telling you you're counting in the opposite direction, but it doesn't really matter for the math. Okay, cool. Does anybody know what the most perfect blackbody radiation spectrum that ever has been recorded is? I thought you said something. I'm glad you asked. Let me tell you what the most perfect blackbody radiation spectrum that's ever been recorded is. Here it is. There is intensity as a function of frequency. The green line is a blackbody curve, a Planck curve at 2.7 something Kelvin. And these red data points with, I think, error bars multiplied by a factor of 100 so that you can actually see them, is the spectrum taken by the Cosmic Background Explorer that was launched in the 90s to map out the cosmic microwave background radiation. So according to the Big Bang Theory, the universe began at a very hot, dense state and has been cooling and expanding ever since. There came a point at which the universe, early on in the universe was opaque. Light couldn't really travel through because there were so many charged particles that they would be absorbed and emitted and absorbed and re-emitted. There came a point where it was cool enough that atoms could form, and electrons got all the free electrons that were running around in the universe got attached to hydrogen atoms or helium atoms, and the universe suddenly went from a charged place to a neutral place. And those photons that were traveling when that happened are still traveling through the universe today. And we can look back and see them. The universe has cooled and expanded, so they no longer are hot, but you can still see that distribution of photons and light streaming through the universe today as the cosmic microwave background radiation. And it has a nearly perfect blackbody spectrum, the most perfect that's ever been measured. So I'm out of time now, but let me just show you. There's actually slight temperature differences from one region of the sky to the other, if you, on the micro Kelvin scale. And it turns out that those fluctuations, when you do a much better job of mapping them out, like we did in the early 2000s from WMAP, give you all sorts of very cool information. In fact, this is a power spectrum of the temperature fluctuations of this particular distribution. So the fact that this peaks at 1 says that the little blobs you see here are mostly about 1 degree in diameter. And it turns out that there's a particular universe that follows this particular power spectrum that tells us how much normal matter there is in the universe, and how much dark matter there is in the universe, and how much, what the curvature of the universe is, and an amazing amount of other things about the universe itself we know simply because of the cosmic microwave background radiation. This is now 7 years old, did it even better. We have a pretty good, look at this thing, down to 0.07. We have the whole thing mapped out. Okay, I'll stop there.